Hello everyone, welcome. This is paper 1 from May 2025 and this is time zone 3. Let's have a look and see what we can do. Alright, question 1 is a 5-mark question. A metal structure on a flat surface is in the form of a right pyramid with rectangular base A, B, C, D and vertex H, which is at negative 0.5, 1.5, and 5. Point A has coordinates negative 2, 0, 0, and point C has coordinates 1, 3, 0. This is shown on the following diagram. All units are in centimeters. Okay, so here we have this right pyramid with this rectangular base. The center of base G is the midpoint of AC. Part A asks us to find the coordinates of G. So G, we're told, is the midpoint of this line segment AC. So we have a few different ways that we can solve this. First, most obvious way would be to use the midpoint formula for 3 dimensions. In this case, we have x, y, and z, so we have 3 dimensions. We could just use the midpoint formula for this, and then there's actually a conceptual way to solve this that I'll show you after this. All right, so going to the formula booklet, here we have our midpoint in 3 dimensions. So remember, in 3 dimensions, we have not only just an x and a y, we have x, y, and a z dimension, so this vertical dimension. Essentially, it's the same as our midpoint in 2 dimensions. In midpoint 2 dimensions, we just have average of x and average of y. Here we have average of x, y, and the average of z as well, the halfway point essentially between 2 other points. So let's go back and write this out. So finding the midpoint of AC. Write out the formula first, and then we'll substitute. So we have x1 plus y1, x1 plus x2 over 2, y1 plus y2 over 2, and then of course z1 plus z2 over 2. We can write this out if we want. We can call this x1, y1, and z1. It doesn't actually matter what we call x1, y1, or z1 in terms of x2, y2, and z2. We could have switched these up and it would have been the exact same. You just have to be consistent. Okay, let's substitute then. x1 plus x2 over 2. This would be 1 plus negative 2 over 2. y1 plus y2 is going to be 3 plus 0 over 2. And then z1 plus z2 is going to be 0 plus 0 over 2. Working this out, here we have 1 plus negative 2, essentially positive and a negative becomes negative. Or if you can imagine you're adding negative 2 to 1, the negative kind of wins out and we have negative 1 over 2. 3 plus 0 over 2 just becomes 3 over 2. And then 0 plus 0 is just 0 over 2, or simply 0. All right, so that would be our midpoint between A and C, and that would give us point G. All right, so 2-mark question. That is certainly a way that we could do this, and they would be asking for some kind of method mark, as in using the midpoint formula. Conceptual way is if we have a right pyramid, we know that the midpoint is going to be right underneath the vertex. So if we know the x, y coordinates of our vertex, we know that the midpoint, this midpoint on the base, is going to share both these x and y coordinates. That is to say, negative 1/2 and 1.5, or negative 1/2, 1.5, 3 over 2 being 1.5. And then of course the z coordinate, since this is on the base, there's no vertical height that we move up or down. This point G is also going to have, well, no vertical height. It's just going to be at the base of 0 as well. So just, I suppose, confirmation as well. Where is this midpoint? Right underneath the vertex. It's going to have the same x and y coordinates, which it does, except it's not going to have any vertical height. And there it is. All right, let's move on. Part B, write down the vertical height hg. So here's h, here's g. We're asked to find, essentially, this length right here. So from the base all the way up to the top. And what they're asking us is, how high is this? What is the height? So height, remember, for 3 dimensions relates to the z coordinate, so right here. And what do we know? We know that g itself has this z value of 0, so we don't move up at all. And from g, going all the way up to this vertex here, we travel through, well, a distance of 5. So I don't want to overdo this question too much, but here is our 3 dimensions once again. We have our x coordinate, we have our y coordinate, it's going this way, and then our z coordinate goes vertical, up and down. So in this case, we start off at 0, and we go all the way up to 5. So if we start at 0 and go up to 5, what distance would we have traveled? What is the height? Well, the height is just 5. So the vertical height of hg is 5. Part C asks us to find the distance between C and H. So the distance between C and H is this edge, this boundary right here. So a few different ways to solve this, but I think the easiest or most straightforward way would just be to use the distance formula in 3 dimensions. That is to say, we have one coordinate point here in 3 dimensions, another coordinate point here in 3 dimensions, and if we just want to find the distance or the length of this line segment, we can just use the distance formula for 3 dimensions. So let's go to the formula booklet and find the distance formula, and then we can just substitute. All right. So here it is. It's right above our midpoint formula. Essentially, it's very similar to our distance formula for 2 dimensions, except now we have x, y, and z. The difference between x, difference between the y values, difference between the z values, and then we square each of those. So let's go ahead and write this out. I think we can write it out under here. So the distance is equal to, what do we have? We have x2 minus x1, difference of the x's squared, difference of the y's squared, and then difference of the z squared as well. So I think we can see this here. Well, only partly, I suppose. Doesn't matter which one we call x1, y1, z1, as long as we're consistent. This is usually called a little abusive because you can't really just switch up your variables like this. But just for the sake of demonstration, if we need an x1, y1, and z1, and an x2, y2, and z2, just the idea that these are interchangeable if we wanted to. Remember, the order doesn't really matter as long as we're consistent. So let's use this as x1, y1, z1, and this is x2, y2, and z2. All right. So I can actually grab this and move it up here. I think there's enough space, just so we can see everything. All right, so here is d. Let's write a square root again. And then x2 minus x1. So this would be 1 minus minus 0.5, that's interesting, squared, plus y2 minus y1, which is going to be 3 minus 1.5 squared, plus z2 minus z1, and this is going to be 0 minus 5 squared. Okay. So now we could go into the calculator, and I suppose that might not be a bad idea. We can put this into the calculator and solve right away, or we could clean this up a little, especially with these 2 negatives right here, just because you'd want to make sure that you put this in absolutely correctly into the calculator when you do it. So I'm actually just going to clean it up a little first. So here we go. 1 minus minus 0.5. Remember, 2 negatives are beside each other. Negative and a negative makes positive. So this would be 1.5 squared. 3 minus 1.5 3 minus a half is just a 1/2 itself. And then 1 minus 5 just becomes -5 squared. Okay. All right, let's go into the calculator and work this out. So here we are. Set up a square root and then input the values. So 1.5 squared plus 1.5 squared. Don't need our brackets, but I'll put them in anyways. And then plus, here we definitely need the brackets because we want a negative multiplied by itself, -5 multiplied by itself. All right, and then the answer in the end, whoops, that didn't work out. A little bit of an error here. There we are. Okay, this looks good. And the answer in the end is 5.43. Okay. D is equal to 5.43. So back to the document, here it is. D is equal to 5.43, and then we should include our units. This is centimeters. All right. So let's go on. Question 2, we have a 5-mark question. The monthly energy consumption X in kilowatt hours of 150 households in Helvetia is shown in the following table. So here we've got a frequency table and it's relating energy consumption to number of households. In this case, for example, there are 38 households that have an energy consumption between 500 and 700 kilowatt hours. Part A. For this data set, use the midpoint interval values to find estimates for first the mean and then the standard deviation. All right, so the mean is the average, and in this case we want to find the average energy consumption for these 150 households. So given that we have this frequency table and it's broken up into these class intervals right here, we don't actually know the consumption of the individual households, but we do know how many belong to each of these class intervals, or how many households are within such and such a range. So for example, there are 38 households that have an energy consumption between 500 and 700 kilowatt hours. We don't know the consumption of the individual households, but we do know the range. So if we wanted to come up with some average or some estimate of, for example, these 38 households, we don't know where or how the distribution kind of looks like in a way. So we don't know if it's clustered towards the low end or if it's clustered towards the high end. But on average, we can assume in general that the number of high values are balanced by the number of low, and the distribution is roughly, not necessarily symmetrical, but that the high values balance out the low values, and that on average, for example, these 38 households, they would have an average consumption of the halfway point, or the midpoint value. Same here for these 45 values here. We don't know the consumption of the individual households, but on average, we can imagine that it is halfway between the lowest and the upper bound, the lowest and the highest bound. All right. So if we can continue to write out the midpoints, we'll have 1,000 here, 1,200, 1,400, and 1,600. Once again, we're creating an estimate, not knowing the consumption of the individual households. We assume that the distribution is roughly equal within these class intervals. So we choose the middle value as a single value to represent the total number of households in this case for each of these class intervals. All right, so now we have two options. We can either use technology or we can use the mean formula. I'll show you how it looks for the mean formula first, and then I think technology is actually going to be a little quicker, so I think we'll use that in the end. So here is our mean formula. Once again, this is x bar, the mean, and it's the sum of the individual values. So x1 plus x2 plus x3, all the way up to xn, however many values are. In this case, there's 150, and it's over n. In this case, there would be, once again, 150 households. So since we have grouped data, we would do something like this. So we would say the mean is equal to, And we say, okay, well, there are 38 households, and on average, for each of these 38 households, their consumption is 600 kilowatt hours. So we would say 38 times 600 plus, we say, okay, well, here we have 45 households, and on average, their energy consumption is 800 kilowatts. So we're adding, okay, we have 45 households, and their consumption is 800 kilowatt hours. And we would do this all the way up till, for example, this value right here, these 8 households, which have a consumption of 1600. And this would all be over 150, the total number of households. And this is what we could do to calculate the average energy consumption for these 150 households. That's going to take a while. Not to say that we couldn't do it, but I think it's going to take a while. So for something like this, I think we can use calculator, one variable statistics, and then just make sure we've listed out our frequency and then, for example, the energy consumption in another column. So let's go to the calculator, see what that looks like. All right, so actually I'm going to get a new screen here. All right, so lists and spreadsheets, we'll set up X and Y, just out of convention by and large. And for here, we'll put the energy consumption values, these midpoints. So for example, it was 600, 800, 1000, and so on. 1400 and 1600. All right, and then the frequency we'll put in Y. So this is saying there were 38 households with an average consumption of 600 kilowatt hours, and so on. So oops, this is 45, 25, 18, 16, and 8. I'm just going to check to see if this is correct. 25, 18, 6, and 8. All right, this looks good. So although we have 2 columns right here, we have an X and Y column, we really only have one variable. The only thing we have is energy consumption. This right here isn't the second variable. This is the frequency or the count that says, okay, we have 38 households, for example, with an energy consumption of 600. So just be mindful when we go statistics and stat calculations, we have 2 columns, but we really only have one variable. The only variable is energy consumption. It's not being compared to number of people in the household or earnings. All we have is this one variable, and it's energy consumption. So let's go ahead and put that in. So where did we put our actual values? We put those in X. And our frequency, we put in Y. That told us the number of households that matched the given variable value in this case. That's all we have. So let's go and press OK. Here we are. And in this case, we wanted to find the mean, which is given by X bar right here. So average energy consumption is 937.33333 kilowatt hours. So let's go back to the document here and write that out. So X bar is equal to 937.3, or to 3 sig figs, 937 kilowatt hours. Okay. In part 2, we're asked to find the standard deviation. So remember, standard deviation is a measure of spread, how spread out these values are in relation to one another. So for this, we can go back to the calculator. So here we are. And you'll see we actually have 2 values for standard deviation. We have sample standard deviation, which is given by the small s, and then we have population standard deviation, which is given by this lowercase Greek s, this sigma. So which one do we use? The sample standard deviation is more conservative, so it's slightly more spread out. It's this idea that we don't have every single value in our universe of data. We haven't measured absolutely everything, so we use this more conservative value. And the population standard deviation in this case is slightly more narrow. This is the idea that we've collected all relevant data points, and we can say things, potentially at least, with a greater degree of certainty. So the population standard deviation is often smaller. So which one do we use? Do we have a sample or a population? Now, it's somewhat confusing because there aren't only 150 households in Helvetia, so you might think this is just a sample of the total set, a sample of our population. But in this case, population doesn't just mean everyone, it means our universe of data in some sense. So in this case, if we only want to know something about these 150 households, then we can consider this our population. A kind of analogy would be if, for example, we were looking at the players on a basketball team, and we could consider this our population if we were only interested in knowing something about the players on a single basketball team, and we didn't want to generalize to the whole league, for example. So in this case, we have 150 households, we've collected data, and we only want to say something about these 150 households. We don't necessarily want to generalize this to all households in Helvetia. So if this is our universe of data in some sense, these are all the values that we're interested in, we consider this or treat this as our population. So in this case, we would use the population standard deviation of 299.45. So let's go ahead and go back to the document and write this out. So standard deviation is equal to, so let's write our Greek sigma. Standard deviation is equal to 299.45 or 236 sig figs, just 299. This is kilowatt hours once again. Okay, moving on. The standard deviation of the monthly energy consumption in another nearby residential area, Eureka, is found to be 95 kilowatt hours. Part B, interpret the meaning of the value of the standard deviation in Eureka in comparison with standard deviation in Helvetia. So, standard deviation itself is a measure of spread. It's not necessarily the case, but if we imagine, for example, that we have a normal distribution, and one of these is Eureka, and one of these is Helvetia. So what could we say actually? Let's imagine this one on the left is, let's say this is Helvetia. And we say it has a mean of 937. So this is the center of our normal distribution. The standard deviation is a measure of spread, and the standard deviation is 299. It tells us how spread out the data is, and this would be Helvetia. And if we want to compare this to Eureka, and imagine that it is, again, modeled by a normal distribution, what could we say? We don't actually know the mean, but we know the standard deviation is a lot smaller. The standard deviation is only 95. And what that means is that Eureka's values would be more closely bunched together. And that's exactly what we could say for our final answer. So monthly energy consumption in Eureka is less spread out than that of Helvetia. And that would be a perfectly good answer. So here it is in the mark scheme as well. Monthly energy consumption is less spread out than Helvetia. Part 3. The water level H in meters in a water tank after T hours of irrigation is modeled by the following function. Here we have the function h of t is equal to 20 over 2t plus 5, where t is greater than or equal to 0. Part A asks us to find the value of h of 0.5. So this is essentially an input-output question. They give us this input of 0.5, and we're going to find the output. Essentially, they're saying if time is equal to 0.5, what is the height of the water tank? So for this, let's actually write this out. So we have h of 0.5, h of 0.5. So normally our function was written in terms of t. Now we'll write it in terms of 0.5. Wherever we see a t, we'll replace it with 0.5. So we have 20 over 2 times 0.5 plus 5. And I guess we can go to the calculator and solve this, but 2 times 0.5 is 1. So we'll have 20 over 2 times 0.5 is 1. 1 plus 5 is 6. 6, or we can write this as 10 over 3, or what could this be? 3.333333 and on. Okay, so what does this mean in practice? After 0.5 hours, the height of the irrigation tank is 3.33 meters. All right. Part B. First part, find the value of H inverse of 2.5. So H inverse of 2.5. Okay. So sometimes inverse questions might seem a little tricky or are often confusing. Really, what an inverse does is it switches around inputs and outputs. It reverses a function. So in this previous question, we had an input of 0.5. We replaced t with this value. What an inverse does is it switches inputs and outputs. So with this function, this inverse function is saying, the output was 2.5, find the input. So here's our function, h of t. We put in values of t, and then we find the output. Here, we're going to switch that around. They're telling us the output was 2.5. What was the input? So really all we need to do, instead of putting in 2.5 in for t, or 0.5 in for t, for example, like we did with our original, we're going to put the output as 2.5 and then solve for t. So here we go. 2.5 equals 20 over 2t plus 5. So once again, inverse function switches around inputs and outputs. Here's our output. What is the input? So let's go to the calculator and work this out using nsolve. So menu, algebra, numerical solve. 2.5 is equal to, set up a fraction, 20 over 2t plus 5, and we'll ask the calculator to solve for t. So the answer is 1.5. So let's go back to the document here. T is equal to 1.5. All right. So I guess we could include our units here, and that might actually help us for the second question. This is 1.5 hours. All right. Part B, this is part 2 of part B. Interpret this value in context. I think this is actually a nice question because it gets to the heart of what inverse functions do, and I guess functions in general. In this case, inverse switches inputs and outputs. We said, okay, our output is 2.5. What's the input? In the context of this real-world problem, what do we have? We have t is equal to 1.5 hours, and then this h value, the output, is equal to 2.5. So what does this mean in practice? It means that after 1.5 hours, the height of this tank is equal to 2.5 meters. So remember, a function again relates inputs and outputs. We put in some value into the function that tells us the output. We can also switch that process around. We can say, okay, here's the output, what was the input? But again, we're always relating these two values together. In the end, after 1.5 hours, the height is equal to 2.5 meters. Okay, part C. In part C, we're asked to write down the range of H inverse. So what is domain and range once again? Domain refers to the set of inputs that we can feed into our function. In this case, the set of inputs of t. T is greater than or equal to 0. Put in any value you want for time, as long as it's greater than or equal to 0. That makes sense. Range is the set of outputs for a function. In this case, that's the height. What are the range of possible heights that this can take? Well, if t has to start at 0, this would be 0, we'd have 20 over 5. The maximum height would be equal to 20 over 5 is 4. And then as time increases, this value, the denominator increases, so we'd be dividing by a larger and larger number. The maximum value for height is 4, and then eventually our irrigation tank is going to empty and the height is going to go down to 0. It's going to come close to 0, maybe never empty completely. But that would be our range. So once again, domain, set of inputs, range, set of outputs. So what does it mean for our inverse, however? Inverse reverses a function. And I think what's most important in this case is if our domain corresponds to inputs, in this case the values of t, and our range corresponds to outputs, in this case, the possible heights that we can take. And we know that the inverse itself reverses things, it reverses a function. If we're asked to find the range of H inverse, the range of H inverse would be the domain of our normal function. So once again, domain and range, when we're talking about our normal H of t, domain is a set of inputs, range is a set of outputs. Our inverse, for example, reverses things. This inverse value says, here's the output, what's the input? So the range of H inverse is not the range of our normal function. Since the inverse reverses things, the range of our inverse is actually the domain of our original function, and that is the inputs. So what are the set of possible inputs for this function? Well, that's t is greater than or equal to 0. And that's the answer for part C. Question 4. Consider the graph of the cubic function f of x is equal to x cubed plus 2x squared minus 4x minus 2. Part of the graph of y equals f of x is shown in the following diagram. So here we have our cubic function right here. Write down the x-coordinate of the local maximum and the local minimum. So what do those things refer to? Local maximum would be the highest point right here, and the local minimum would be the lowest point right here. They're not the absolute lowest point or the absolute highest point, because for this cubic function they don't actually have an absolute lowest or an absolute highest. So we call these the local max and local minimum, or these turning points right here. So to find these out, we can do this two ways. I think the easiest way would actually be to graph this and then use our max-min functions. So let's go ahead and do that. Here is our graphing calculator, and let's put in our function right here. So this is x cubed plus 2x squared minus 4x minus 2. Looks good. We might need to adjust the window. Actually looks okay. So let's find the maximum first, the local maximum. So we'll go analyze graph, and we'll find the maximum. Choose our lower and upper bounds. So here we have the x and y coordinate. The x coordinate is -2. Let's actually find the minimum once again, and then we'll go back to the document. So analyze graph, find the minimum, sweep over, and this is 0.666667, or 2/3. All right, and that would be the x coordinate. Okay, so let's go ahead and write this out. So here we are back at our document. I'm actually going to put both of these and then write out the answer. So there's this point right here at -2.6, and then there's this point right here, which is, we can write it as 2/3 or 0.6661 and -3.48. Okay. They only want the x coordinate, so for the local minimum, that would be 0.666. And for our, you might say, okay, what about for 3 sig figs? 6667 is okay as well. And this is our local minimum. And our local maximum is right here. And the x coordinate there would be equal to -2. All right. Part B, hence write down the interval where the function is decreasing. So this hence always tells us that we need to make use of what's come before. And in this case, it's actually a nice clue. Sometimes it's constraining, but in this case, it's a nice clue. So here we have the function increasing. Here it's decreasing and then increasing again. So what is the interval where the function is decreasing? Well, when x is greater than -2 and less than 667, I suppose, then our function is decreasing. And you might ask, hey, why not when x is greater than or equal to? Well, when x is greater than or equal to, when x is equal to -2, this is actually going to be a straight line. It's going to be parallel to, in this case, the x-axis. So it's actually not decreasing when x is equal to -2. Only when x is greater than -2 and less than 0.667 is it, strictly speaking, decreasing. All right. The tangent to the curve 1, -3 is parallel to the straight line y equals 3x plus 5. Part C, write down the gradient of the tangent and the equation of the tangent. So let's find out where 1, -3 would be. 1, -3 might be somewhere, maybe around here, I suppose. So we can imagine that this is, we can imagine at least that this is the point 1, -3. And they tell us there's a tangent. A tangent to the curve is parallel to the line y equals 3x plus 5. Y equals 3x plus 5 is actually somewhere up here, but we know that this tangent is parallel to it, so it has the same slope. So if they're asking us about the gradient of the tangent is parallel to this line right here. This line right here has a slope of 3. So the gradient of our tangent as well must have the same slope of 3. Okay. Last part, part 2, we want to find the equation of the tangent. So we want to find an equation in terms of y equals mx plus b. We already know the gradient of this tangent line. It's 3. So we have y equals 3x plus b. Now we just need to find this y-intercept right here. So how can we do that? I think the easiest way would actually to use this value that they give us. They already give us a point on the line, which is 1, -3. If we can substitute that into our equation, then we should be able to find the value of b here. So let's go ahead and do that. So x is equal to 1, y is equal to -3. So y is equal to -3, x is equal to 1, and now we just have one unknown b. Since this point, this xy point lies on the line, it's a solution, and then it should balance this equation. Now we just need to find b. We can do that just using a little algebra. You can end solve this as well. In the end, we would have -3 is equal to 3 plus b. Remember, moving this to the other side, it becomes negative. This is going to be -6 is equal to b. B is equal to -6. And in the end, we'll have an answer of y is equal to 3x plus, or in this case, b is -6. So we have 3x minus 6. And that would be our answer in this case. Looking back at this, if we wanted to, here's our tangent line. Imagine that it is just touching this line, and it looks like a y-intercept of -6 looks pretty good. So there it is. Part 5 is a 9-mark question. A telecommunications company has identical cell towers in a rural area. They are located at the points A15, B78, and C412. The coverage areas are divided as shown in the Voronoi diagram. All distances are in kilometers. So here they give us the points A, B, and C. Find the equation of the perpendicular bisector of AB. So here's AB. We want to find this edge, this boundary line right here. Perpendicular bisector of AB. All right. I kind of like these questions. They actually show up fairly often, and at least in terms of the set of steps that we need to follow, they are they're always the exact same actually. So this is a nice one to have kind of in your back pocket. So to find the equation of a perpendicular bisector when they give us 2 points, the procedure is find the midpoint between the 2 points, find the slope of the line between these 2 points. With that slope, we want to find the perpendicular. So just multiply by -1 after switching the top and the bottom of that fraction, and then after that substitute that original midpoint. So let's go ahead and work this out. So first let's find the midpoint between a, b. The midpoint is given by the average of the x's and the average of the y. This is in our formula booklet as well. So x1 plus x2 over 2, y1 plus y2 over 2. In this case, it's between a and b. Let's actually label these and then write out the values. So here we are. This is 1, 5. This is 7, 8. And now we can call this x1, y1. Call this x2, y2. And let's substitute. So x1 plus y2, 1 plus 7 over 2. And y1 plus y2 is going to be 8 plus 5 over 2. All right, this is going to be 8. 8 over 2 is equal to 4. And this is going to be 13. 13 over 2 is equal to 6.5. Okay, so that would be our midpoint. We might want to keep this as a fraction, but we'll see. Okay, so now what is our next step? We want to find the slope between a and b. So to do this, we'll use our our slope formula. Remember, m is given by y2 minus y1 over x2 minus x1. This is change in y over change in x. We've already written these values down, so let's go ahead and substitute. This is going to be y2 minus y1 over x2 minus x1, or in this case, 8 minus 5 is 3, and then 7 minus 1 is 6. This will actually just be 1/2. You can also draw triangles if you want. I think that's sometimes a nice way to work things out, and just do rise over run like this, if you wanted to. I think I've done this in some other videos, so maybe not entirely necessary, but here it is all the same. If we're at 1 and we go to 7, we've traveled a distance of, use a new color I guess, we've traveled a distance of 6, and same, if we're at 5 and we go up to 8, we've traveled a distance of 3. And then if we want to say rise over run is equal to 1/2. I think that's also a nice way to work it out if we wanted to. All right, I'm going to erase that for now so it doesn't clutter things. Okay, so we have the slope of AB, but we're not entirely interested in finding the slope of AB, not directly. What we really want to find is this perpendicular bisector, and for that, it's going to be perpendicular to this AB. So we know what m is. M is equal to 1/2. And what is m perp then? What is the perpendicular? Well, remember in this case, we switch the top and the bottom and then multiply by -1. So 2 over 1 and then multiply by a negative. So we have -2 over 1 or just simply -2. All right. So we know the slope of this line, it's equal to -2. So we're almost there. We're kind of just at the last stretch, I suppose. So let's find the equation of this perpendicular bisector. It's an equation of a line, so it's going to have this form of y equals mx plus b. We already know the slope. The slope is equal to -2. So y is equal to -2x plus b. The only question left is, what is this y-intercept? Looks like it's maybe somewhere around here if we were to just continue this line, but that's not necessarily going to be good enough. So what do we have? We have some equation, and we have x, y, and b. B is the only thing we need to find here. That's what's left for us until we can write an equation. But we already have an x and a y value here. We have a point on the line, which is the midpoint. The halfway point between these lies on the perpendicular bisector. So since we have a point that lies on the line already, we can actually go ahead and substitute into our equation, and then we'll move from having 1, 2, 3 unknowns We'll get rid of these x and y's and we'll just have b as an unknown. That's how we can solve. So let's input these values for x and y right here. So x is equal to 4, y is equal to 6.5. So 6.5 is equal to negative 2 times 4 plus b. I'm going to move this over just a little. All right, we can go ahead and end solve this, but I'm going to work this out just with algebra a little. 8 plus 6.5 is going to give us 14.5, and that's going to be b. So altogether, we have y is equal to this negative 2x. We already knew the slope, plus, and b is equal to 14.5. All right, and that looks pretty reasonable, we once said. Just bringing it back. Okay. Equation of perpendicular bisector, y is equal to negative 2x plus 14.5. I think these are nice questions just because, first off, they're very common, or they're fairly common. And also, procedurally, they have the same set of steps, and I think it is kind of intuitive. Find a point on the line, that's the midpoint. How do we find the perpendicular? Well, first we need to find the slope between these 2 points. Use this to find the perpendicular. We know the perpendicular. Now let's substitute an xy value that we found originally, and then we can use that to find b, and then we're done. Okay, so a nice 4 marks. All right, question 5, continued. The company is planning to improve the coverage of its cellular network in the area by adding 2 new towers. It identifies potential locations at the point D, 8.2, and E, 14.10. The company reviews the coverage areas and draws a new Voronoi diagram. Identify the correct Voronoi diagram from the options shown in the following diagrams. Okay, so what do we know about a Voronoi diagram? We know that each cell represents points that are closer to a given site than any other. So for example, here we're closer to E, or at least if this is the correct one, we should be closer to E than to B. Similarly here, we're closer to D than we are to either B or E. So that's what these cells represent. These boundary lines are points that are equidistant, that is to say the same distance from, well, any point. So for example, this B and E, all points along this boundary line should be an equal distance from the sites B and E. So if we were to, for example, plot a point right here, any point really, this and this should be equal. Same here. If we were to plot another point right here, all points on this boundary line should be equal to, or an equal distance from both of these sites, B and E. So boundary line represents the set of equidistant points from these 2 sites, from these 2 sites, from these 2 sites, respectively. And the last thing we can generalize and say that any given vertex or vertice should, by definition, be an equal distance from all 3 of these points. So remember, along this line, all of these points are an equal distance from B and E, and that should be no different when we get to the end right here. So these 2 should still be equal. And generalizing that further, all points along this line should be an equal distance from both B and D, and that should not be any different once we get to this endpoint. So once we get to an actual vertex or vertice right here, they should be an equal distance from all three sites. So let's see which of these pass the test. So option 1 actually looks okay for now. There's nothing that's really maybe kind of jumping out as incorrect, at least at the moment. So let's go to option 2 first. And option 2, we can see right away that this boundary line is definitely not an equal distance from B and E. Looks pretty good for C, looks maybe okay for A and B. This looks pretty good, but definitely not. This is definitely not the same distance as this. So for this, we can say option 2 is not correct. Option 3 again, let me actually see if I can maybe zoom so we can look at all of these at once. Option 3 actually looks potentially okay as well. There's nothing really that is maybe too bad. For example, this boundary line looks good. These points look like they're an equal distance from all of these once again. So there's nothing that's kind of like jumping out right away. Option 4, right away we can see, yeah, this boundary line definitely isn't an equal distance between B and C. So this isn't going to work. So let's compare option 1 and option 3. So what's the difference between these two? This line looks the same. This line looks the same. This line actually looks somewhat the same, but this vertex isn't the same, and this line isn't the same. So just looking at it, is this equal distance? Is this actually perpendicular to this? Offhand, it doesn't actually look like it. Here, for example, this looks more perpendicular to this. This boundary line looks perpendicular to A and B. So offhand, this looks good. One thing I think that we can use to actually test it is this idea that all 3 points must be an equal distance away. So let me see. We can write this out. So each of these, that looks pretty good. And one thing that doesn't entirely look correct in this case, it looks pretty good for B and D, but this line A looks a little too far. And if we wanted to, one thing that we can do, which is I think kind of nice, is if we draw a circle, stretch it out, it should be equal. It's not something, I don't think you'll have a compass, for example, on your test, but this is the idea that a vertex should be an equal distance from all of these. And it looks like it satisfies B and D, but not A, for example. So this is a good one. This one doesn't satisfy all of the requirements. So the correct Voronoi diagram would be option 3. Okay. Let's continue on. Each tower provides guaranteed excellent coverage within a radius of 3 kilometers. Pooja is at a beauty parlor located at the point 6,4. Part C. State whether excellent coverage is guaranteed for Pooja at the beauty parlor. Justify your answer. So I'm not actually a fan of this question in a certain way because it's unclear which Voronoi diagram to use. These are the telecommunication towers that are currently built out. And so the question is, should we plot 6,4 right here and ask, is the distance greater than or less than 3 kilometers? Or should we plot the point 6,4 here and ask whether this is less than or equal to 3 kilometers? Really, this is a plan, which means that it's not built out yet. So to ask the question of Pooja whether she would receive guaranteed excellent coverage, well, it's not quite clear whether we should use the hypothetical situation of these are currently built out, or whether we should use the state of things on the ground as they are now. Because the answer would actually be different. Here, I worked this out earlier, she would not receive excellent coverage as the state of things are right now. But the question is, would she receive excellent coverage in option 3? I don't actually think it's clear, to be honest. My first inclination would have been to use the state of things as they are right now, plot 6,4, and find the answer. But here, looking at the mark scheme actually, they're asking us to use the planned implementation. That is to say, with the given telecommunication plan at the moment, would she receive excellent coverage? And I don't think that's entirely clear, at least with this question itself. State whether excellent coverage is guaranteed. At the moment it isn't, but if the plan is implemented, then that's a question that we can ask. So here it is, a little, I think, ambiguous in interpretation, but they are asking us to use the plan instead of the state of things as they are right now. So let's go ahead, plot this point 6,4. Here it is. Let's label it 6,4. So Pooja is within this cell right here, cell D. That means she is going to be closest to this site right here, site D. And the question is it less than or equal to 3 kilometers? If it's less than 3 kilometers or equal to 3 kilometers, she'll receive excellent coverage. If it's anything more, then she won't. What we want to find then is the distance between 6,4 and D, which is at 8, 2. Two different methods we can use. We can use the distance formula, or we can draw a triangle. I think it's actually nice to use Pythagorean theorem for this case. So if we just look at a right angle triangle, for example, and we can say, what is the distance or the length of each of these legs? If this is 6 and we go to 8, the length of this leg is 2. Similarly, looking at the y coordinates, if we're at 2 and we go to 4, the length of this leg is 2. And now we can just use a squared plus b squared equals d squared. What would that mean? That would mean that 2 squared plus 2 squared is equal to d squared, or 4 plus 4 is equal to d squared. 8 is equal to d squared. I'm not interested in finding d squared, but just d. Take the square root of both sides. Therefore, d is equal to root 8. And then going to the calculator and asking, for example, is root 8 greater than or less than 3? We see that root 8 is equal to 2.828 or 2.83. So, going back to the document here, d is equal to 2.83. We also know this because 3 squared is equal to 9. So, well, let's say root 9 or greater is greater than 3. Anything less is less than 3. So, what do we have? We have 2.83 is less than 3. Therefore, she would receive excellent coverage. I think using the Pythagorean theorem is a nice way to work this out, but if you want, of course, you can always use the distance formula as well. And here it is, x2 minus x1 squared plus y2 minus y1 squared. And then substituting those values, 8 minus 6 squared plus 2 minus 4 squared is equal to 2 squared plus negative 2 squared, or once again 4 plus 4, root 8, which is approximately 2.83, which itself is less than 3, all the same. Okay, so either way, I think sometimes drawing triangles is a nice conceptual way, but you can definitely use the distance formula as well. So in this case, she is less than 3 kilometers away, therefore she will have excellent coverage. All right, question 6, 9-mark question. 3 points N, P, V are shown on the following diagram. NP is 20 meters, PV is 25 meters, and VPN is 55.5 degrees. All right. Find NV. So this is NV right here. We want to find a side length. 3-mark question. I think this is actually a nice question. It's kind of decontextualized and abstract, and to be honest, I actually think it's pretty straightforward. So what do we have? We have a non-right angle triangle. We're in the realm of non-right angle triangles. We want to find the side length 3 right here, this NV, and we have 2 options. We can essentially use the sine rule or the cosine rule. Sine rule is the easiest to apply. Let's see if we can use it. If not, then we'll have to use the cosine. Sine rule is angle opposite side length, and then we see right away we don't have any other angles to pair any of these opposite side lengths to. So that is not going to work. Cosine rule, remember, is 1, 2, 3 side lengths and an opposite angle. In this case, we have everything we need for the cosine rule. So in this case, we can use the cosine to find this missing side length. Let's write out the cosine formula. It is in our formula booklet, but I'll write it out here. It is a squared equals b squared plus c squared, just like the Pythagorean theorem. but then it has this little addition here, negative 2bc cosine. Remember cosine rule, the one kind of tricky part is this variable, or this value here, the subject of our equation that we're trying to solve for in this case, is paired up with this value right here. Remember, these large angles, or these large letters, are degrees, and the smaller letters are side lengths. So in this case, when we have a side length that we're trying to solve for, we need to make sure it is lined up with, or that it matches rather, that it matches the side length that we have. All right, let's go ahead and substitute here. So a squared, we don't actually know. That's nv. We can call it x, or a, doesn't really matter. Let's call it x for now. X squared is equal to b squared plus c squared. 20 squared plus 25 squared. Minus 2bc minus 2 times 20, 25. And then cos A, what is the opposite? It is 55.5 degrees. 55.5. Okay, so we have everything we need. Let's go into our calculator and we can actually end solve this. So clear the screen. Menu, algebra, numerical solve. Let's use x. X squared equals 20 squared plus 25 squared minus 2 times 20 times 25. We'll multiply this by cos 55.5. Okay, that's the calculator to solve for x. Make sure you're in degrees, and I think we're good. Okay. So the distance, or the side length, is equal to 21.4. So 21.4 meters. Let's go back to the document and write this out. X is equal to 21.4 meters. All right. 21.4 meters. Okay. So we'll just clean this up. I have a feeling we're going to need to make use of this. Next, we want to find PNV. So first off, what are they asking for? They're asking for this n, where the top hat is, PNV. We're looking to find this theta value right here. All right. So now we can ask ourselves, we're still in the realm of non-right angle triangles. We're going to need to use the sine rule or the cosine rule. Sine rule is generally a little easier, or a little more straightforward. It's quicker at least. What do we need? We need angle, opposite side length, and now we have angle, opposite side length. So we should be good. Angle, opposite side length, angle, opposite side length. Let's use sine rule. So here's our sine rule. Sine rule is sine A over A is equal to sine B over B. In this case, this theta is what we already have. So let's go ahead and substitute. Sine theta over, remember this A and this A, they're paired together. So the opposite is 25. And we have sine B. Sine B, we'll use these two, I guess, this angle and side length pair. Sine 55.5. And it is paired with 21.4. Okay, let's go into the calculator and we'll end solve this again. So, menu, algebra, numerical solve. Didn't work. Okay, set up a fraction. And we'll write sine, we'll have to call it x for now, I suppose. And then we'll write this over 25 equal to, and then we'll write sine 55.5 and do this over 21.4. Ask the calculator to solve for x and make sure you're in degrees. So here it is, 74.3 degrees. Let's go back to the document and write this out. Theta is equal to 74.3 degrees. Let's replace this. I think it's always not a bad idea to complete the information for our diagram, because chances are we might actually need to make use of it. So 74.3 degrees. Last question, part C. Hence or otherwise, find the shortest distance between P and NV, which is kind of a nice question. So what do they mean, the shortest distance between P and NV? NV is this line segment right here. So this line segment NV, where on this line segment are we closest to point P? So if you were somewhere along this boundary line right here, at what point would you be closest? At what point would you be closest to P? And then what is that distance? So you can just imagine you are somewhere along this line. By intuition, it looks something like this. This might be the closest. But why? Any line, so we know the shortest distance, or the shortest path to some point, is always going to be the straight line, or the perpendicular to the base. So something like this, if we can draw an altitude in some sense from the highest point down to the base. So perpendicular to the base would be the shortest point. Another way to conceptualize this is, again, actually with a circle. So if we, for example, imagine this, where is the point where we are the closest distance? I guess if the circle was a little better, maybe it would be something like this. But where are we closest? Well, when we're directly perpendicular, when we can walk in a straight edge from this line segment NV. So what we want to find is this distance right here. And we can call it T, I suppose. So how can we find this side length right here, this D? Good question. We've just created a new triangle. Before we had this non-right angle, we just created this triangle right here. We've just created a right angle triangle. And with that, we know one angle, we know one side length, and now we just need to find this side length right here. So we actually moved into the realm of right angle trigonometry. And in this case, we have a side length, we have an angle, an opposite side length, and a hypotenuse. So what do we have? I'm actually just going to erase this and make some room. Let's see if this works. Okay. So what do we have? We have an angle, an opposite side length, and a hypotenuse. So we have opposite and hypotenuse. So remember, a SOHCAHTOA sine is opposite over hypotenuse. So in this case, we have sine theta equals opposite over hypotenuse. Let's write out what we know. We know that theta is 74.3. Opposite itself is D, the side length that is opposite. And then our hypotenuse, our longest side length, is equal to 20. And then we can do a little algebra to solve this, or we could once again use nsolve. Let's actually use nsolve to work this out. So menu, algebra, numerical solve. Sine 74.3 is equal to, and then we have d over 20. Create a fraction, d over 20. Ask the calculator to solve for d. We're in degrees. 19.25, so 19.3 meters. All right. So going back to the document here, d is equal to 19.3 meters. Once again, we're on this line segment right here. What's going to be the shortest path? The one that's perpendicular to this line segment. With that perpendicular, we've just created a right angle triangle. We know 2 out of the 3 unknowns that we need. So we have opposite hypotenuse, that's sine theta, substitute, and then we can solve. All right. Okay. Question 7, 5-mark question. The loudness of a sound L, measured in decibels, is determined by the intensity of the sound, I, measured in watts per square meter. The relationship between loudness and intensity can be expressed using the logarithmic function L equals 10 log base 10 I over I naught, where I is greater than 0. Where I naught is the reference intensity, that is to say the intensity of the least audible sound to the human ear. The reference intensity I naught is 10 to the negative 12 watts per square meter. The intensity of sound on a busy street is 10 to the negative 5 watts per square meter. Calculate the loudness of the sound. Okay. So sometimes students get a little, not necessarily intimidated, but potentially confused, or logarithmic questions sometimes seem daunting, but I don't think that's necessarily the case, or it doesn't need to be. By and large, especially for applications interpretations, a lot of the log questions are actually input-output questions, or variations on that. And this is one that is essentially an input-output question. So it's just being mindful of our variables, what they refer to, and then just making sure that we can identify and then use the function or the formula correctly by substituting. So let's see what we're asked to find. We're asked to find the loudness of the sound. So L right here. So we have two variables, I and I naught. I naught is 10 to the negative 12. This is the reference intensity. So we know this value, and we know the intensity of sound on a busy street. So what is the loudness of the sound on the busy street? That's given by I. I is the intensity of the sound. This I is equal to 10 to the negative 5. And with that, we have these two variables that we need, and we can actually go ahead and substitute, and then simply solve for L. So let's write this out. So L is equal to 10 log base 10 I. I right here is the intensity of the sound. And the intensity of the sound is 10 to the negative 5. And this is over I naught. I naught is 10 to the negative 12. And just like that, we've substituted all the key elements, and we can actually go ahead and solve. So if you want, you can actually simplify this, and then we can work this out if you're comfortable with logs, or we can, to be honest, we can just end solve. Here it is if you want to look at the algebraic work. So this would be 10 to the 7, and then this would be 10 to the log base 10 to the 10 to the 7. Essentially ask, what do we need to raise 10 to for it to become 10 to the 7? Well, we need to raise it to the power of 7. And in this case, the answer is 70. But to be honest, I'd imagine if you get to this point right here and everything's already substituted, you probably can just go to the calculator to work it out. And let's actually go ahead and do that. So here we are. Get a new screen. And we will write 10 times, and then here's our log right here. Log, and this is log base 10. So in the original question, it had that subscript 10, that's our base. And then here we're going to want to get a fraction. And the first top, the numerator, was 10 to the negative 5. And the denominator was 10 to the negative 12. All right, there it is. And there's our answer of 70 once again. And it's a decent way to do it as well. All right, going back to the document. Here we go. So the loudness of the sound is 70, and loudness, does it say what our loudness is measured? It's measured in decibels. So right here. Loudness is measured in decibels. Okay, let's go on. The sound of a jet engine reaches a loudness of 185 decibels. Determine the intensity of its sound. Give your answer in the form of A times 10 to the k, where A is greater than or equal to 1, less than or equal to 10, and k is an element of the integers. That means positive, negative, whole numbers. No decimals, no fractions. Okay, so in this case, remember a lot of logarithm questions are just input-output questions. Here they gave us inputs and they asked us to find the output. Here they're giving us an output. They're telling us what L is, and we need to find this value of this I, the intensity. Okay, so let's go and work that out. Let's put in what we know using this function right here. So L, we know what L is. It's equal to 185. So 185, 10 log base 10. And then let's make sure that we've got I and I naught correctly. I naught is the reference intensity, and they told us it was the least audible sound. This one's always going to be the same. This reference intensity, I naught, it's the baseline which we measure against. So we know this is 10 to the negative 12. Essentially, I believe we're asking how many times louder is it than the base intensity of least audible sound. And I is what we're trying to solve for. So the intensity of the sound, which is given to us right here, intensity of the sound. Okay, so now we've got an equation. We just have one unknown. We can go to the calculator and solve for this. So let's go ahead and do that. Menu, algebra, numerical solve. 185 equals, then we'll set up the function once again. 10 log 10. Turn this into a fraction. We want to find what I is, and we know the reference intensity is 10 to the negative 12. Ask the calculator to solve for I, and I think we should be good. Okay, so here we have 3.16228, and then this is a common mistake, this e to the 6. So it's not like 3.16, and the calculator is saying, hey, this just goes on for another 6 decimals or anything like that. This e, you can kind of think about it as an exponent, or 3.16228, and this is times 10 to the 6, times 10 to the 6. So it's a calculator notation which kind of condenses information. So let's write this out in the document. So here we have 3.16228, but 3 sig figs 3.16, and it's times, and we don't just write e to the 6, we write times 10 to the 6. And that is it. That's all we needed. I will actually show you one thing in the mark scheme, which I think is a nice reminder to maximize process. So here's the mark scheme, going all the way to this is question 7. Question 7 right here. So here's C. Where is it? Attempt to solve the logarithmic equation using graph or solver analytically. This part right here. So you can get potentially 2 out of 3 for an incorrect answer written correctly in the required form. So going back to this question originally, what are they assessing? They're assessing, an understanding of logarithms and inputs and outputs, but they're also assessing an understanding of scientific notation. So even if you get a correct answer, but you put it into the correct form of scientific notation, that's still showing an understanding on at least one of the concepts they're assessing here. So you can still get partial marks, even if you're not sure. I guess the idea is show as much of your understanding as possible. Question 8. Prakash is the leader of a customer service team and is interested in determining whether there is a relationship between a customer's satisfaction level and the type of service interaction they have experienced. He collects data from a random sample of 250 customers and tracks their satisfaction level after 3 types of service interactions: in-person, online chatbots, and website contact forms. He categorizes the satisfaction levels as satisfied, neutral, and dissatisfied. He records the data in the following table. Okay, so here we've got this two-way table, the satisfaction level, satisfied, neutral, dissatisfied, and then the type of service they received, in-person, online chatbot, or website contact forms. Prakash performs a chi-squared test for independence at the 5% significance level. The critical value is 9.488. The null hypothesis, H0, is the satisfaction level and the type of service interaction are independent. So null hypothesis, satisfaction level, type of service are independent. State the alternative. So remember, null hypothesis and alternative always have this kind of generic form. Satisfaction level, or blank and blank, are independent, or blank and blank are not independent. And in this case, satisfaction level, and this is kind of lengthy, type of service interaction, essentially the exact same thing, they're either dependent or they're not independent. So it's an either or situation. So if the null is status quo, they are independent. The alternative, which is given by H1, is that satisfaction level and type of service interaction are not independent. All right. Find the degrees of freedom for this test. Degrees of freedom, remember, is given by row -1, column -1. In this case, we have 1, 2, 3 rows, 3 -1, and 1, 2, 3 columns. So 3 -1. In the end, this is going to be 2 times 2, or 4 degrees of freedom. Okay. Part C, we're asked to find the chi-squared test statistic. Okay, so for this, we'll actually just go to the calculator, set up a matrix, and then find the chi-squared test statistic, chi-squared value. So here we are. So first, let's set up a matrix. Menu, here we want to go into matrix, create matrix. Number of rows was 3, number of columns was also equal to 3. Let's input the values, 35, 30, 23, and so on here. 39, 23, and lastly 19, 28, 22. I'm going to make sure these are correct just real quick. Looks good. Now let's define our matrix. So control var, and we'll call it A, I suppose. Make sure it's in. There we go. Now we're going to run a test. So statistics, let's go into stat tests, and we want a chi-squared two-way test, not a goodness of fit, just an independence test. What is our matrix? It is A. All right, so now we have these 3 pieces of information which we often want. Degrees of freedom, we already found. P-value is important, but here we want to find the chi-squared value, which is 3.319 or 3.32. So let's go ahead and write that out. So going back to the document here, I'm going to move this aside. So our chi-squared, it's a little funny, but I think that's fine. Chi-squared calculated statistic is 3.31, or 3.32 actually. 3.32. Okay. Let's go on. Prakash concludes that there is sufficient evidence to reject the null hypothesis. State whether Prakash is correct. Justify your answer. And then part 2 asks, write down the conclusion for this test in context. Okay. So, there is sufficient evidence to reject the null hypothesis. So can we really reject the null hypothesis? We have 2 things that we can work from. We can work from the significance level, or we can work from the chi-squared test statistic. I think a lot of students are sometimes more comfortable working with the significance level. So start with that, and then we'll go on to the chi-squared test statistic. So let's go into p-val and p-crit. Let's ask this question. The p-value that we found and the critical value or the significance level. So going back to the calculator screen for a sec, the p-value that we found was 0.506. 0.506. So here we are at the document once again. P-value is 0.506. As a percentage, that's 50.6%. Our p-crit was 5%. In this case, our p-value is a lot higher than p-crit. What does this mean in practice? It means that we'll see these kind of numbers in terms of survey responses, I suppose. We'll see these numbers 50.6% of the time just based on chance, which is almost like a coin toss in a way. So it's not particularly convincing to say that there's some kind of interaction between the variables, because going out and collecting data, we're going to see these results 50.6% of the time. So it's not too confusing, or not too convincing rather, that there's actually some kind of interaction. So remember, in this case, p-value higher than p-crit. In this case, we accept HO. So, or sometimes nicer actually, is that we say we fail to reject. We say we fail to reject the null hypothesis. So p-value greater than p-crit, chance of occurrence really, really high. It's not too convincing that these things are actually relating to each other or influencing one another. So we accept the idea that they're independent. Okay. But what about the chi-squared value? The chi-squared value and our chi-squared critical value right here. So let's compare this, our chi-squared calculated, and then the chi-squared kind of critical value. So the one that we calculated, our chi-squared value right up here is 3.32. So here it is, 3.32. And our critical value, the chi-squared crit, let's actually call it chi-squared crit, I think that's nice, is 9.488. All right. So sometimes students think this is confusing because they're kind of inverted, but I think once you understand the concept and what they signify or mean, then it becomes a little easier. So in this case, our chi-squared value, the calculated, is less than the critical value. What does chi-squared value measure? It measures the difference between the observed and the expected. So essentially, is there a strong difference between what we observe and what we would expect just based on chance alone? So we found that the chi-squared value is 3.32, which is very, well, actually it's significantly below our critical value. Chi-squared value is the measure of difference between the observed and the expected. What we found is we don't have a significant level of difference between the observed and the expected. So just based on what we would expect on chance alone, our observed values don't differ all that much. This is the amount of difference that we would need in order for us to say, hey, there's something going on, there's something unusual. If we have a chi-squared value that is greater than our cutoff point of 9.488, and we can imagine this as the amount of difference, the difference that we're willing to tolerate. If we have a chi-squared value that's greater than 9.488, then there's more difference than we're willing to accept. And at that point we say, hey, beyond a reasonable doubt, it seems like these two variables are influencing one another. But the chi-squared value of 3.32 says, hey, there's not actually a lot of difference between what we would expect and what we're observing. So it doesn't seem like these two variables are really influencing each other. So our chi-squared value in this case is less than our crit. And once again, we would say, they accept the idea that these things are independent and not influencing each other. So is Prakash correct in this case? No, because we don't reject the null hypothesis, we accept it. And what is the conclusion of this text in context? Is that, well, in this case, it is the null hypothesis. That is to say, satisfaction level and type of service interaction are independent. That's what it would be in the real world context. That would be part 2. Question 9. Pasquale owns a company that produces and sells curry powder. The rate of change of the company's profit, P, in Mauritian rupees from producing X kilograms of curry powder is modeled by dp over dx is equal to negative 10x plus 460, where x is greater than or equal to 0. So in this case, we have change in profit over change in number of kilograms sold, and number of kilograms sold, x, has to be greater than or equal to 0. She makes a profit of 3,300 Mauritian rupees when producing 10 kilograms of curry powder. Part A asks us to find an expression for the company's profit, P, in terms of x. Okay. So a number of questions on IB AISL papers are often iterations or variations on a common type. And sometimes the more papers that you do, actually, you'll get more comfortable or familiar in recognizing these types. In this case, they've given us a derivative, and essentially what we need to do is find the original function p. So sometimes we'll get a function and we'll be asked to find the derivative. In this case, they're giving us the derivative, change in profit over change in kilograms sold, and we're asked to find that original profit function. So we have the derivative, we've got a point on the original function, which we're going to need to use. Can we find that original function? All right, let's go ahead and write out this function and see how we can tackle this. All right, so I want to actually write it on a few lines lower, and I hope you'll see why. So dp over dx is negative 10x plus 460. So in this case, we have the derivative, but we want to find the profit function, not change in profit over change in kilograms, just the profit. Okay, so how can we do that? We have this in our formula booklet. We have two different, we have two formulas. We have the derivative and then the integral. So the derivative is, if let's say f of x is equal to, actually let's write it in the abstract, xn, then the derivative is equal to, what do? We multiply out in front, and then we reduce this value right here by 1. That's our derivative. But what about if we have some function, for example, and we want to reverse the process? Let's say we have some function, and it's equal to x to the n. What if we want to find the antiderivative in this case? Well, in this case, we would reverse the process. So instead of taking away 1, we would add 1 to our exponent. And instead of multiplying out in front, as we do here, we would, reversing the process, divide by whatever this exponent is. So, I'm not sure, maybe I can clean this up a little bit. This is x raised to the power of n plus 1 over n plus 1. That's how we take our derivative. Add 1 to the exponent, and then divide by whatever this value, this new value of the exponent is. And this would take us from a derivative to a normal function, or essentially it's just the process of taking an antiderivative. So let's try that here in practice. So let's go term by term. This is negative 10x. Let's go ahead and write out negative 10 x. There's actually a 1 here, of course. We don't actually write a 1, for example. I guess we assume that it is given, I suppose. If there's nothing there, then we assume that it is a 1. So x is raised to the power of 1. Let's add 1 to that. Now it's raised to the power of 2. Remember here, we have this n plus 1. We're going to also want to divide by whatever that new exponent is. So let's divide by 2. All right? Plus 460. Now there isn't really any x here, but remember when we take a derivative, for example, if we have something like f of x is equal to 3x, the derivative of this would then be just 3. So the x falls away as we take a derivative. If we want to reverse the process and take an antiderivative, we would then add an x. a kind of maybe strange way to look at it is if we think this is x to the 0, now we have x to the 1, but I think just making sure knowing that an x falls away and that we would need to bring it back to reverse the process is fine. And then lastly, which is sometimes maybe, what can we say, forgotten step, is potentially there was a constant here. So once again, if we create just like a fictional derivative, let's say we have f of x, and now let's say it's 3x plus 2. If we want to take the derivative of this is going to become 3, and then our constants just fall away, right? So in this case, we actually don't know. We don't know if there was some constant here originally. So to deal with that, we would just write c, so some constant. So let's clean this up just a little. I'm actually going to bring this down now. Then let's clean this up. So p is equal to negative 10 over 2 is negative 5 x squared plus 460x plus c. One nice thing is that if you ever want to make sure that you did it right, you can just take the derivative of your function and see if you actually get back to your derivative. So multiplying out in front is negative 10x. X falls away is at 460. This constant would fall away and we would get this. Okay. Last thing for this 5-mark question, we want to find out what c is. What's the constant? In this case, we have 3 unknowns: profit, number of kilograms sold, and then the constant. We know 2 out of these 3 things. We know the profit when she sells 10 kilograms. We can substitute and then solve for this missing unknown. So let's go ahead and do that. Profit is equal to 3,300 when 10 kilograms are sold. Now we've got an equation just in terms of c. Let's go ahead and solve this. All right. Menu algebra equals negative 5 times 10 squared plus 460 times 10, times 10 plus c, and then we'll ask the calculator to solve for c. Just make sure this is all correct. This looks good. Okay. So the value of this constant is negative 800. C is equal to negative 800. So let's go ahead, go back to the document, write this out. C is equal to negative 800. Putting this all together, for this function right here, we can replace c with negative 800. And this will be our function, or I guess cleaned up a little. We can also write it like this, right underneath. Okay, so this is our function. And let me actually go ahead and grab this just so we can write it at the end, because I believe we might need to use this again. So here's our profit function. All right. Pascalia decides to increase the production of curry powder from 25 kilograms to 50 kilograms. Find the increase in profit. Okay. So in this situation, originally they produced 25 kilograms, and then they are going to now produce 50 kilograms. What would be the increase in profit? We've already got a function which relates profit to number of kilograms produced. So in this case, we should be able to actually find the profit at 25 kilograms, the profit at 25 kilograms, and then also the profit at 50 kilograms, and then find the increase. So essentially what we would be doing, I'll write this out, I suppose here. Essentially what we would be doing is we would find P50 and the difference between P50 and P25. So let's go ahead and find P50 first. P50 is equal to we use this function right here. Negative 5 times 50 squared plus 460 times 50 minus 800. I'm actually going to find P25 as well. And this is just going to be negative 5, 25 squared plus 460, again substituting 25, and then we can find out P25 as well. All right, so let's go to the calculator and work these out. So it's going to be negative 5 times 50 squared plus 460 times 50 minus 800. All right, and then I think I'm going to do this, and I'm just going to replace this with 25. And here is the profit for 25 kilograms produced. Okay, so let's go back to the document here. In this case, we have, I'm going to write this out, for P50, the answer is 9,700 Mauritian rupees, and for P25, it's 7,575 Mauritian rupees. So, if we want to go back to this original question and ask about P50 minus P25, or change in profit, that would be 9,700 minus 7,575. And in this case, the answer is 7,575 is 2,100 or 2,125 Mauritian rupees. Okay. And that would be the change in profit from 25 to 50 kilograms of curry powder. Question 10. The times in seconds for the fastest 16 women in a 50-meter freestyle swimming championship event were recorded. All swimmers recorded different times. Part of a box and whisker diagram for these times is shown in the following diagram. So here we have the swimming times in seconds, and it looks like they give us Q1, they give us the median, or Q2, and Q3. We don't know the max or the min. Part A, write down the number of swimmers who took more than 24.70 seconds to complete the race. So this is a 1-mark question, we just need the answer. So remember, for a box and whisker plot, it divides a data set into quarters or quartiles. So we have 25% here between the minimum and Q1, 25% here, 25% here, and then 25% here between Q3 and the max. So if there were 16 women in total, we could expect 1/4 of the data set to be within each of these sections. So 4 women here, 4 women here, 4 women here, and then another 4 swimmers here. So 24.7, this marks Q3. We could say that there were 4 swimmers that took more or had a greater time than 24.70. So in this case, the answer is just 4. All right. Part B, find the interquartile range, the IQR, for the data. This is a 2-mark question. So IQR is actually given to us in the formula booklet, IQR, interquartile range. And this is given by Q3 minus Q1. And let's actually mark those values on this box and whisker plot here. This is Q1. This is Q2. We often call it the median. And this is Q3. So the distance between Q1 and Q3 is the IQR. Maybe I'll write that just a little lower. This is our IQR. So let's find the bounds of Q3 and Q1, and then we can work out this, this arithmetic kind of statement right here. Q3 looks easy to read. It's 24.7, so let's write that out. And Q1 we might actually need to do a little work. It's not quite 24.3, it's slightly less. So our intervals are from 24.2 to 24.3, and they're divided up into 5 sections. So 1, 2, 3, 4, 5. So if this is a distance, maybe I'll zoom in a little. if this here is a distance of 0.1, 0.1 is being divided up into 5 intervals. You could put this onto your calculator if you want, but that would be 0.02. So each of these are 0.2 greater than the last. So 24.2, 24.22, 0.24, 0.26, 0.28. So this would be 24.28, this line right here. So let's go, and here we have 24.28. And that's our statement for the IQR. Now we can go ahead and work this out. So what would this be? This would be 0.42. So you can go onto the calculator and work this out, or we can just work it out arithmetically, I suppose. So what's the difference here? 0.42 seconds. All right. Moving on. An outlier is defined as a value that satisfies one of the following: more than 1.5 times IQR below the lower quartile, so right here, or more than 1.5 times IQR above the upper quartile. Of the 16 women, the 2 fastest swimmers took 23.96 and 24.12 seconds, and the 2 slowest women took 25.12 and 25.40 seconds to complete the race. Part C, we have 2 questions. Part 1 says, show that only one of these times is an outlier. All right, so let's plot these values just to get a sense of things, and then we'll see which one is the outlier. So let's plot 23.96 and 24.12 first. All right, 23.96, here's 23.96, and 24.12 would be right here. I'm actually going to move this down just to put it on the same line. All right. Let's do the same for these, 25.12 and 25.40. So 25.12, it's all the way up here. And then 25.40 is all the way here. Okay. So just by inspection, these of course are further away than these. So you might have reason to believe that this is the outlier, but since there are 4 marks for this question, you might need to show some process. So how can we determine whether something is an outlier or not? Let's first look at the lower quartile, the bounds for what an outlier would be, and then what the bounds for the upper quartile, or sorry, the outlier for, I guess the upper range would be. So I'm going to move this away and we'll set up some equations. So 1.5 times IQR below the lower quartile. So if we have Q1 right here, it's going to be Q1 minus 1.5 times IQR. That would be the bounds for the lower quartile, or sorry, the bounds for the outlier on the lower half of this box and whisker plot. And the upper bound would be Q3 plus 1.5 times IQR. Okay, so I'm going to work this out horizontally. Usually I think it's nicer to work it out in a column form, just going step by step by step. But just to save space, I think I'll write it out like this. Okay, so Q1 minus 1.5 times IQR. Q1 we know is, we found it to be 24.28. 24.28, and then minus 1.5 times IQR. I'm going to bunch this step actually. So let's go to the calculator for a sec. And let's go 1.5 times IQR. And the IQR was 0.42. So this is 0.63. 0.63. So 24.28, going back to the document here, minus 0.63. And Q3 plus 1.5 times IQR, let's find the bounds for these outliers on the, I guess this is the slowest times. Q3 plus 1.5 times IQR, this is going to be 24.7, plus, and then this is going to be 0.63. So let's go to the calculator and work these out. So here we are. This is going to be, let's find the lower bounds first, 24.28 minus 0.63. And then let's find the upper bounds while we're here, 24.70 plus 0.63. All right, so anything that's below this line or this value of 23.66 is an outlier. Anything that's above this point of 25.33 is an outlier as well. So let's go back to the document, write these out, and then we'll work from there. So lower bound, 23.66, upper bound, 25.33. Okay. So show that only one of these times is an outlier. So I guess graphically, we could just plot these really quick. This is maybe a little excessive, and you probably wouldn't want to do this on a test, but just to visualize, 23.66. 23.66 actually doesn't even show up. It'd be somewhere down here. So there's definitely nothing beyond this. So there's no outliers at the lower end. But what about this 25.33? 25.33 would be about halfway between this line right here, something like that. And of course this bound is above. This is above that upper bound, where something either would not be or would be an outlier. So how can we potentially write that? Show that only one of these times is an outlier. We could say that 25.40, which is the slowest time, the maximum time that someone took, is greater than Q3 plus 1.5 times IQR, or greater than 25.33. So only one of these times is an outlier, just this one. Of course, the second value here of, 25.12 is less than 25.33. So it would not be an outlier. All right. Part 2 asks us to complete the box and whisker diagram above. So I think this question is actually a little more challenging than it might seem on the surface. So let's go ahead and look at the box and whisker plot. So the box and whisker plot, remember, we'd have our minimum value, Q1, Q2, Q3, and then the maximum. But it's a little more challenging up here because we have an outlier. So the question of how far do we extend these whiskers is, I guess, maybe the question we have to deal with. Let's start with the lower bound here. So box and whisker stretches all the way to the minimum value. So not all the way to what the outlier would stretch, but just to the minimum value. So here we know our minimum value is 23.96, or right here. So let's stretch the whiskers all the way to this value of 23.96. All right. And what about the upper end? We can't exactly, or we wouldn't exactly stretch the whisker all the way to the maximum, because in this case the maximum is an outlier. So to distinguish, or to show that something is an outlier, we can either put an X or an asterisk or so. So let's put an X here. And in terms of the whiskers, we stretch only to the maximum value that is not an outlier. So in this case, it would stretch to 25.12, which is this value right here. So we don't go all the way to the outlier, we just go to the highest value that is not an outlier. And we know that this is the highest value, that there's nothing in between here, because these are the two slowest times, and each of the times themselves are different. Okay, so there it is. Good. All right. Question 11. Sophia takes out a loan of 50,000 euros. She pays a nominal interest rate of 4.2% per year, compounded monthly. She must pay back the loan in 25 years through regular monthly payments made at the end of each month. Part A. Find the amount Sophia must pay back each month. Give your answer correct to 2 decimal places. Okay, So since they're making monthly payments, where is it? Right here. So she's paying back the loan through regular monthly payments. We can't use the compound interest formula. We're going to need to use a financial solver. So anytime someone's making incremental payments, we need to use a financial solver. This is paying back a loan or even contributing to a pension fund or something like that. We only use the compound interest formula when we put money into an account and we just leave it there. Then we can use the compound interest to see how it grows. In this case, we're making monthly payments, so we're going to need the financial solver. So I'm actually going to go ahead and write out each of these values for the financial solver. You can skip ahead if you like. So this is part A. We're going to want to find values for n, I, present value, PMT, final value, payments per year, compounding periods per year, and then payment at the end. Okay, so let's go ahead and fill these values in and then solve for the unknown. Okay, so let's start off. I think the easiest one to always start with, the most straightforward one, is interest rate. So she's paying 4.2%. Present value, in this case, is $50,000. Generally, we use the convention of money flowing in, money flowing out. In this case, Sophia has the money in her hands in some way, so we can write that as positive. PMT is the monthly payments. We don't actually know how much she's going to pay, so let's leave this empty. The final value, in this case, she wants to pay off this loan, so in the end, the final value of the loan goes to 0. Payments per year, she's making regular monthly payments. So in this case, there are 12 payments per year, and compounded is compounded monthly. All right, so N refers to total number of payments. So it's a 25-year loan, and she's going to make monthly payments. So N is always connected with PPY, payments per year. So in this case, she's going to make 12 payments over 25 years, and this would be equal to 12 times 25 would be equal to 300 payments. So let's write that out. Okay, so now we've got everything we need. Let's go to our financial solver and work this out. So N, I think it's always nice, actually, you can do this, 25 times 12, and then it will give you the value of 300 as well. Interest rate, 4.2. Present value, 50,000. We don't actually know PMT. That's what we want to find. Final value is 0. That looks good. Payments per year is 12. Compounding periods is again 12. And payment she pays at the end of each month. All right. Everything looks good here. $269.47. So that's how much she must pay back every month. Let's go back to the document. Here we are. So this is $269.47. Here they tell us 2 decimal places. In general, for financial mathematics questions, we want to write to dollars and cents. So let's write out the answer right here. 269.47, and the units are euros. Okay. At the end of 8 years, Sophia wins the lottery and pays back the remainder of the loan early in one single payment. Part 1 of Part B. Find how much Sophia pays back in the single payment. Give your answer correct to 2 decimal places. Okay, so we can actually use a lot of this information that we have here. So what I'm going to do is essentially I'm actually going to copy this and write this out for Part B. So let's write this out. I'm going to move this. And we can use a lot of this for Part B. All right. Clean this up. Payment, we actually know how much she's paying each month. She's paying negative 269.47. But what do we want to find out? She wins the lottery at the end of 8 years. So how much is left on the loan? What's the final value after 8 years? Now we need to find how many payments she would have made after 8 years. So let's modify this a little. What can we keep? The interest rate is still the same. The initial size of the loan, the payments we know, and then the compounding period and the monthly payments that she makes. That's all the same. But we want to find out how much she owes at the end of 8 years. And for that, we're going to need to know how many payments she's already made, the number of payments. So in this case, PPY is always connected with N. So in this case, she has made 12 payments over 8 years. Altogether, she has made 96 total payments. So let's go ahead and find the final value of this loan after 96 payments. So there it is. That's what we want to find, this final value. Okay. So here we are. Let's go to our document, the calculator here. 8 times 12, 96. Interest rate is still the same. This is good. This we might actually run into trouble. The calculator gives us essentially a greater number of decimal places than what we were working with initially. Right now we're imagining it's $269.47. But the calculator actually gives us these finer decimal places right here. And if we use the full accuracy, then we'll actually get a slightly different answer for final value. So for this, since it is a new question, I'm actually going to delete these decimal places to the right and write out just the monthly payment as calculated for that first part of this question. All right. So 96 payments, 4.2%. Initial loan is $50,000. This is good. Let's find out the size of this loan at the end of 8 years. Okay. So $39,243.42. 42 cents. That's what she owes at the end of 8 years, and that's what she's going to pay off in one big payment. So let's go back to the document and write that out. So this is 39,243 euros and 42 cents. And so the answer for how much she pays back in the single payment is going to be this value right here. 39,243 euros, 42 cents, and then let's put the euro symbol once again. Okay. Part 2. Find the amount of money find the amount of money saved by Sophia by paying back the loan early. Okay, so this is kind of an interesting question. If she were to pay it back in these small incremental payments of $269 or thereabouts over this 25 years, she would pay it off slower and she would have to pay more interest. So this $50,000, the bank is charging 4.2% interest, all the while, so long as she has the money and the bank doesn't, the bank is going to want to charge a fee for the service of lending her this money. But if she pays it all back at once, then she is done paying back the loan. She has no more loan and she no longer needs to pay interest on it. If she pays interest on the loan for an extended period of time, she has to pay more money. If she can pay it off early, then she saves some money on interest. So let's first find out how much she would pay if she paid it off over 300 payments, that is to say over 25 years. So let's find out this value. So what can we say? Let's call this total. Let's call this, what can we say, T25, the total over 25 years. What would that be? Well, that would be Sarah or Sophia? Sophia. Sophia is paying 300 payments, and each of those payments is 269 euros and 47 cents. So that would be the total amount that she pays. The payments don't increase or decrease, they stay constant, and she makes 300 of them That is to say 12 every year for 25 years. So let's work out how much that would be if she were to just keep to the original agreement or the original terms of this loan. 300 times 269.47. So she is paying off 80,841. I'm going to go and check the float here, just because I think there might be some decimal places hanging off towards the end. So I want to recalculate this actually. No, it's exactly correct. So 80,841. That's the total amount she would need to pay. Okay. Let's go back to the document and write that out. So she pays $80,841. And that would be the case if she didn't pay it off early in any kind of way. All right. But now, how much would she pay what is the total amount that she would pay if she just keeps the loan for 8 years? For this, we know she makes some final payment of $39,243.42. But how much has she paid before that? Well, she made 96 payments of $269.47. She's already made 96 payments, and then she paid this off. So the total amount is previous payments plus final lump sum. So let's go ahead and work that out. So this will be 96 payments of $269.47 plus this final lump sum payment of $39,243.42. So let's go to the document with the calculator and find out what that is. 96 times 269.47 plus 39,243.42. And in this case, the total amount would have been $65,112.54. So let's write that out. $65,112.54. All right, good. So what is the savings? Savings is equal to, well, what she would have originally paid minus what she paid after, if she were to just keep it for 8 years. Essentially the difference between these two. So let's write that out. I don't think you would need to go through and write this out actually on a time test. I think just keeping these two values and then the final answer would be enough for method marks. But just to show you what's going on here. All right, let's go to the calculator and work that out. So here is the original amount. I'm going to copy paste this minus the 8-year amount. And in the end, she has saved $15,728.46. So that's the difference between the 25 years of payments and just the 8 years of payments. So let's go and write this out. This is $15,728.46. And once again, this is in euros. Okay, there it is. Question 12. This is a 7-mark question. A team of researchers is using a model to predict the relative happiness of different countries. To do this, a value x is calculated based on easily measured parameters, for example, life expectancy or available social support. It is assumed that higher values of x indicate greater happiness. To test the model, a survey is conducted in 6 countries, A, B, C, D, E, and F. In these countries, the level of happiness is assessed directly using questionnaires and given a score y out of 10, with higher scores indicating greater happiness. To select the countries for the survey, all countries are divided into 3 equal groups based on wealth, and 2 countries are chosen randomly from each group. Part A asks us to write down the name of this sampling method. Okay, so we have a number of different countries, and we are going to just sample part of this population, or the population of total countries. We're just going to sample 6 countries. Okay, so the countries are divided into 3 equal groups based on wealth, and 2 countries are chosen randomly from each of those groups. All right. So since we're taking the total population and we're dividing it up into 3 equal groups, in this case, we're dealing either with stratified or quota sampling. How can we tell whether it's stratified or quota sampling? Well, what we do after the fact. So after we've grouped them, are we using random or non-random sampling? In this case, we use random sampling, so we're in the realm of stratified sampling. If we were to use non-random sampling after we divide it up into groups, then we would be in the realm of quota. So in this case, we've divided it up into groups. It's either stratified or quota. Since we're doing random, we're doing stratified sampling overall. So this is stratified sampling, I guess we could say. All right. The results of the survey, along with the value obtained from the model, are given in the following table. So here we have the countries, the value from the model X, and then the happiness score Y. The researchers will accept the model is valid. The researchers will accept the model as a valid predictor of happiness score if the Pearson's product moment correlation coefficient R is greater than 0.8. Part 1 of Part B, they ask us to find the value of R. Okay, so this is just standard correlation. I think one thing, maybe I'll say this is probably, I'd say, one of the strangest final questions that I've seen on a paper 1, because usually they get more and more challenging. This could almost be, to be honest, a question that appears in the top 3. So I think it's a good idea to use the 5-minute reading time always, and then check out where your kind of familiarity lies, or your kind of core competencies, and so what you're most comfortable with. Because this is actually not a bad question, and it's very peculiar that it's the final question, because they're usually like some abstract calculus question or some kind of involved, maybe geometry question, and so. But this one is fairly straightforward, and to be honest, it's actually just, as far as I see, a kind of straightforward correlation. So here we go. Part B, Part 1 of Part B, find the value of R, correlation. Let's put these values in for X and Y into our spreadsheet, and then we'll find R. All right, here we go. Spreadsheet, set up X and Y. Let's put the X values in. So these are the values from the model: 12.3, 15.2, 14.1, and so on. 20.1, and then 19.2. Let's find the corresponding happiness scores for each of these. 7.3, 6.2, 6.9, 8.0, and then 7.2. All right, I'm just going to check to see if these are all correct. 2, 14.1, looks good. And here, this looks good as well. All right, we're comparing 2 variables here. So let's go stat calculations, run 2 variable statistics. X's are within X, and the Y's are within Y. Scroll down and find R. R is equal to 0.8538 or 0.854. That's the strength of our correlation. So let's go back to the document. R is equal to 0.854 for Pearson's correlation. So, part 2, hence, state whether the model can be regarded as a valid predictor of happiness score. So it's only valid if the Pearson's product moment correlation is greater than 0.8. So is it valid? We could say yes, valid. And since it's state, it's just, well, one answer, that should be fine. But just to be safe, we could say 0.84 is greater than 0.8, and that should be fine. All right, part C, find the equation of the regression line, y on x. Again, fairly straightforward. Let's go back to the document and we'll run a linear regression. So here we are, menu, statistics, stat calculations, linear regression, y equals mx plus b. X and y. Let's find m and b. There it is. Okay, so the slope is equal to 0.266, so 5/8 rounded to 3 sig figs. And then we have 2.3957 or 2.40 rounded to 3 sig figs for the y-intercept. Okay, let's go back to the document and write this out. The equation of the regression line, y equals 0.266 x plus 2.3957 or 2.40. Okay. And again, a kind of particular or a kind of strange final question. Rounding off, for a particular country, x equals 17.2. Use the regression line to predict the happiness score of this country. To be honest, it's probably the strangest final question that I've ever seen, I have to say, on a paper one, just because this is a rather straightforward question. This is essentially an input-output question. We have a model which links happiness score to this model x, this parameter here. We have an input, and we're just asked to find the output, that is to say the happiness. So let's write this out. Y is equal to 0.266 input of 17.2 plus 2.40. Let's go ahead and work this out on the calculator. 0.266 times 17.2 plus 2.40. So the happiness score, at least the one we would predict, would be 6.975 or 6.98 to 3 significant figures. So let's write this in. 6.9752 or 6.98. Okay. The question continues on the following page. That's it. Okay. Like I said, a kind of strange way to finish. Almost seems like it's been added on in a kind of like post hoc way, just like, thrown on at the end, almost like they were unsure what to add. The ordering is very strange, but I think that says 5-minute reading time. Just make sure to time manage, because sometimes the questions don't necessarily get more challenging as the way they go through. Okay, that's it for now. I hope it was helpful, and as always, best of luck. Take care.